All right, you have made it to one of the most important parts of all of calculus, and that is the first derivative test. So it's part kind of the mean value theorem if you want to kind of go into a theoretical type of way to look at this. But essentially what ends up happening is when you have a increasing function, the slopes of those lines are positive slopes. And when you have a decreasing function, the slopes of those lines are negative slopes. And so if we know things about f prime, if we know f prime is positive or negative, then we know if the function is increasing or decreasing. What that then will find us is when we find the zeros, because that would be between a positive or negative, then we're going to be able to find relative maxes, or if ours a change from negative to positive, a relative minimum based on critical values and evaluating things in the first derivative. We'll be able to know things about the original function. So the first derivative test says that if f prime changes from positive to negative, then you must have a local maximum. That goes right along with what I just drew in that diagram, and that's what we'll practice today. If f prime changes from negative to positive, we have a local minimum. If there's the same sign, then f of c is neither a maximum or a minimum. All right, so let's use the first derivative test to find the local extrema for this function f of x, and it's a cubic function. So I'm going to take, this is going to be the steps that we do. You take the derivative, 3x squared minus 6x minus 9, and we want to find the critical points first. Let's factor out a 3. X squared minus 2x minus 3. And I'm going to go ahead and factor this into x minus 3, x plus 1. And so I know that I have two candidates, two critical points at x equals 3 and x equals negative 1. Here's what we're going to do next for the first derivative test. We're going to put this on a number line. And I'm just going to worry about the x values. So I'm going to say negative 1 and 3. Now I know that f prime is 0 at negative 1 and at 3. My question is f prime positive or negative between those critical points? Now, I personally like plugging into the factored form because all I care about is if it's positive or negative. So I can choose anything to the left of negative 1. So let's choose like x equals negative 10. If I plug in, this is always, 3 is always positive. If I plug in negative 10, I get negative 13. And I get negative 9. So a positive times a negative times a negative. Just to show you that mathematically, just on this one example, I get 3 times negative 13 times negative 9. So I have a positive times a negative gives me a positive. Therefore, f must be increasing on that interval. All right, let's choose a number between negative 1 and 3. Let's choose x equals 0. Well, again, 3 is always positive. If I plug in 0, I get a negative and a positive. So a positive times a positive must be negative, meaning f must be decreasing on that interval, and I must have a local maximum because f is changing from increasing to decreasing, and f prime is changing from positive to negative. All right, let's choose a number bigger than 3. Like we can choose 10. Okay, choose numbers that you feel like you can confidently plug in. So 3 is always positive. This is going to be positive. This is going to be positive. So when I multiply those all together, I get a positive, and I have a minimum. So that's where we're going to find our local extrema on our graph of f, analytically or like algebraically, if you will, using the derivative. Now, another thing you could use is you could be like, oh, this is a quadratic that opens up and has 2 zeros. So f prime must have positive outputs 0, negative outputs 0, positive outputs. So then that could help you find your like sign here on your number line test. And then you could then match it to our increasing, decreasing here. It says for us to look at a graph of this just to verify what's going on. All right, and then I see here that I do have a relative maximum at x equals -4. I do have a relative minimum at x equals 3, and this is a cubic function with positive slope. So it makes sense that this would be the graph here. Okay. All right, let's look at another example. So I have f of x equals 5 times x to the 1/3, so the cube root of x, minus x to the 5/3, so the cube root of x to the 5th. It's already written in power rule ready form. That's very kind of them. So let's go ahead and find f prime. So that's going to be 5 times 1/3, 5/3, x to the -2/3, minus 5/3, x to the +2/3. Oh, why did I put an x there? Sorry about that. 5/3. All right, so this is going to be 5/3 x to the 2/3 minus 5x to the 2/3 over 3. Now I do want to make this have a common denominator. We're going to have to do some algebra work here. So let's multiply this by x to the 2/3 over x to the 2/3. And in the numerator, I'm going to have 5 minus 5 x to the, multiply like bases, add the exponential powers, multiply like bases, add the exponential powers. Now remember, for critical points, I want to find where f prime is equal to 0 or undefined. So for equal to 0, I'm going to look at the numerator. And I'm going to see that this is undefined at x equals 0. Now that's an important point. Something is going on there. I'm going to include that in my number line test, in my first derivative test, and we'll kind of investigate that with a graph. So let's figure out the factors here first. So 5 times 1 minus x to the 4/3 equals 0. Now since this is a cube root, and a 4th and all of that on the inside, let's kind of evaluate that. That seems a little bit tricky. So if x equals 1, yes, that is 0. What happens if x equals -1? Here, I'm going to give me a little more room. If x equals -1, yeah, if I take it to the 4th power first, then it becomes positive. I cube root it, yep, that works as well. So x equals -1. It's always a little bit tricky, right, when you have the like power functions. I kind of just choose that. Like it looks like x squared minus 1, so let's verify and see if it's both of these, and it is. All right, so I'm going to put all my critical points here on my number line test. And again, I'm going to evaluate f prime at these points. Now I'm going to pull up a calculator just because there's the square roots and all of the fourth roots and the cube roots. And so I'm going to use a calculator to find these actual values. And that's just going to save us some time here. Now remember, we want to find values of f prime, right? Values of f prime. So I want to know, is f prime positive or negative? That's what I want to find here. Now, of course, I could just graph it and we could look at it right here, but just stick with me, okay? 5, I'm going to put this in parentheses. 5 minus 5, let's let x be equal to like -2. To the 4/3 all over 3 times -2 to the 4/3. Okay, I get a negative number. So that tells me that f must be decreasing, right? All right, I gotta plug in now something between -1 and 0. Let's plug in -0.5 for x. Oh, I get a positive. Yeah, so that was a good thing to check, that was going to be one of my critical points there. Okay. Now let's just plug in positive 0.5. Okay, well, it's because when you take the numbers to the 4th power, they're making them positive. So this is going to be like a mirror image. Something interesting is going on this one. All right, and then let's plug in 2. Now I think it's going to be negative because I think they're going to be mirrors, right? Yep. And then it's like, what the heck is happening right here? Well, what do we know is true about the parent function of x cubed? Or not x cubed, excuse me, the cube root of x. Before we just jump into a graph. It does this, right? Where I don't end up having a definition for my derivative right there, like f prime's undefined. And there's no maxes and mins because the function's like always increasing, but I still have that critical point, that point of interest at 0. So I'm thinking my graph, how it changes is it dips down to have a minimum, still has that vertical tangent line here at 0, stays increasing with a maximum, and then comes back down. That's my best guess based on only knowing things about parent functions and translating it to this here of what this might look like. All right, let's see. Let's go back up to our original function. So I plug it in correctly. Let's just see what it looks like. Y equals 5x to the 1/3. See, there we go. There's 5x to the 1/3. Minus x to the 5/3. All right, so I didn't have my end behavior correct, but I did have these parts correct. We'll talk more about how we can know things about concavity, although it's concave up this whole time, so that doesn't really help. But it does kind of help to see like that modification of the parent function graph of cube root of x and how that might kind of wiggle a little bit different there through the origin.